Hello everyone and welcome into yet another live stream. Sorry for that. Oh, my mixer wasn't plugged in. Hi there everyone. Hi there Joshua. Hi. Today is gonna be a bit of a shorter live stream, I think. Because I finally finished rendering everything, all of it. And I can finally make some more videos. It feels great. But today we will be obviously doing the same thing we've been doing for ages now. It feels like this. Let me switch to dark mode. There. Should be better. Alright, also refresh this one. No. Will we get a preview? Oh, the video's up. The one I've been rendering, it's up on YouTube already. That one is already up. Now I just need to work on the other ones, the actual videos, because this was just a start to the series. Ni hao is what I meant to say. Well, oh wow, it's a lot of calculation. Well, but those do seem simple. Okay, so more about kinetic molecular models. So that's what we're learning, right? We're learning about them gases and stuff. So, grab it. And there you are. Music. Neat. By SodaKC Music at youtube.com/@SodaKC Music. Anyhow, let's get into it then, shall we? Well, I don't really like the fact that when I'm not speaking... Hold on, first of all, let me just move myself aside. When I'm not speaking, the cup appears to be empty. But I do seem taller for some... Maybe I'm off, but it seems like I'm taller this time. Anyhow, let's get into the kinetic molecule theory. Festive, that's fun. We're gonna have fun. We're having fun. Okay. So, how long, by the way, till we actually get to the meat and potatoes? And by meat and potatoes, I mean electricity, electronic stuff. Well, electricity, not really electronic. Electronic, that'll be chapter 4. We're 1-6. Chemical bonding, that's cool. Crystallography, treason. That's a lot. That's a lot. Okay, hold on. How large is this textbook? It's massive. Oh, that's a good thing, but can we have a poll first? Yeah, first, yeah, insult me and then ask for a poll. That's no for you. That's no for you. Diffusion. That's a lot of background. Okay, so electrical properties. That's third one. So the one I'm interested in, which is this one, which will give us a semiconductor and transistors, it's touch, MOSFETs, you know, all the good things. That's the third chapter. We're still in the first one. Alright. Kinetic molecular theory. Let's get into it, because... fun. Alright. Velocity of gas molecules. Well, yeah, we're trying to run through it a bit at least. Yeah, averages. Wide range of values. Yeah. Velocity comes here since the answer is not very useful. We need to do our averaging. So there we go. This instead find the average, the squares of the velocities, then take the square root of this value. The resulting quantity is known as a root mean square or RMS velocity. Okay, makes sense. So we have the root mean square velocity, in which equation, if I may. There we go. Velocity of root mean square is equal to s squared t fraction divided by n, and then at the top we have sigma v squared. Neat. So, which we will denote simply as v bar. Okay. There we go. I can't retype. It's difficult stuff. The formula relating the root mean square velocity, temperature, and molar mass is surprisingly simple. Considering the great complexity of the events, it represents 3RT, in which m is the molar mass in kilograms per mole, and k is... Wait, what is k? Hold on. Okay, so R is a constant? What is the channel about? Just science. We're doing science and... Okay, so R is the constant. Right? Am I reading this correctly? K, the gas molecule is responsible for the constant. Okay. What's T, if I may ask? T is the absolute temperature and M is the molar mass of grams. Okay, sick. Good night, guys. Good night, Carrara. Good night. So we can denote this as having the root mean square. Wait, is this root mean square? Why is this just V? Is this average molecular energies? Is this inconsistent notation or is this a different thing? The age-old question. Okay, let's just assume it's inconsistent notation and this should be just bar V. I think so. It would make sense. It would be kind of silly of us to just switch to a completely different topic, right? And this is just an example. Okay, so this would be then equal to M and T, where T is the absolute temperature and M is the molar mass. Neat. Where should I start from? Honestly, wherever you want. Any of the most recent videos will do. There isn't really that deep of a plot. Probably whatever seems to interest you most, that's also a good answer, yeah. Do you like AIs, quantum mechanics, math, computer science? Start with whichever one you like. The new one is really good. And the new one is just an introduction to a series. I didn't rate it. I really... It's entertaining, I would say. Alright, Boltzmann distribution. As always, I'm really careful history, because we're trying to go as quickly as we can. The derivation of Boltzmann curve is a bit complicated to go in here, but its physical basis is easy to understand. Consider a large population of molecules having some fixed amount of kinetic energy. As long as temperature remains constant, this total energy will remain unchanged. Makes sense. But it can be distributed among the molecules in many different ways, and this distribution will change continually as the molecules collide with each other and the walls of the container. Okay. I would say addition to quantum bit. Yeah, that's the bit everyone's seen, basically. And the addition to quantum is decent. Alright, so we have flow energy states. So this happy compromise, I love calling it the happy compromise. Okay, so we have... Well, this is all very descriptive, actually. There's nothing for me to comment on. However, this kinetic energy is equivalent around in discrete amounts, which are known as quanta. Okay, so once the molecule has given a number, of kinetic energy quanta, these can be among different directions of motion in different ways. Distinct total velocity state for the molecule. The greater number of quanta, that is the greater total kinetic energy of the molecule, the greater number of possible velocity states. If we assume that all velocity states are equally probable, then simple statistic predicts that higher velocities will be more favored simply because there are so many more of them. Makes sense. Okay. Yeah, so more high energy states are available. Although the number of possible higher energy states is greater, the lower energy states are more likely to be occupied. This is because only so much kinetic energy to the available to the gas as a whole. Yes, so each particle has the same probability of having any amount of kinetic energy. And as a sum, they need a certain amount of kinetic energy. But it's more probable for particles to have lower amount of kinetic. Am I am I explaining it well? I don't think so. I could explain it with animation, but well, it's not really a video, is it? This is because only so much kinetic energy available as a whole. Every molecule. Okay, so let's note this down. Might as well. So we have this image. There we go. And we'll have this list. So first, we have lower energy states are more likely to be occupied because there is a certain amount of kinetic energy to go around. Then second, so there's so all of these summed together have a certain amount of energy. That's why lower are more likely because there's a limit. Second, if all velocity states are equally... Okay, I actually don't know why it's going up. Oh, never mind. I get... Okay, I get it. Because direction. Makes sense. Okay. Equally the probable... Then higher velocities are... if all velocity states, then higher velocities are more probable because they have more velocity states. I am rewarding this a bit to my liking. Alright, distance to even out the kinetic energies in a collection of molecules then shows that there are always some molecules whose instantaneous velocity is near zero. The net effect of these two opposing energies, one favoring high kinetic energies, the other favoring low ones, is the peaked curve. So this red right here. Notice that because of the asymmetry of this curve, the mean average velocity is not the same as most probable velocity, which is defined by the peak of the curve. At higher temperatures over light molecules, the latter constraint becomes less important, and the mean velocity increases, but with a wider velocity distribution. The number of molecules having any one velocity diminishes and the curve tends to flatten out. Uh-huh. Okay, I would really welcome an example right now. Higher temperatures allow for larger fraction of molecules to acquire a great amount of kinetic energy, causing the Boltzmann plot to spread out. Okay, so the higher the temperature, the more spread out this shape is. Okay. The higher the temp, the more spread out. Okay. Notice as the left ends of the plot are anchored at zero velocity, there will always be a few molecules that happen to be at rest. As a consequence, the curve flatten out as the high temperatures make additional high velocity states more accessible. Okay. The area under each plot is the same for a constant number of molecules. Okay. Makes sense. The dark mode is messing up the plot a bit. I'm not Okay, well, I'm gonna switch just for this side because it screws up all the CSS. All molecules have the same kinetic energy at the same temperature. So the fraction of molecules with a higher velocities will increase as m, and thus the molecular weight decreases. Okay. So the higher the molecular weight, the lower wow, that's a wild sentence. my brain is having a really hard time analyzing some of these. All molecules have the same kinetic energy at the same temperature. Okay, all molecules have the same kinetic energy at the same temperature. So the fraction of molecules with higher velocities will increase as m, and thus molecular weight decreases. And thus molecular weight refers to m, right? Which means this would just mean with high velocities will increase as m decreases. So as m decreases, the fraction of molecules with higher velocities increases. Right? The reading is the toughest part. Makes sense from this equation, doesn't it? Doesn't it? What's m again? M is the molar mass. Yeah. So all molecules have the same kinetic energy at the same temperature. So the fraction of molecules with higher velocities will increase as m, and thus molecular weight decreases. So fraction of molecules with higher velocities. Fraction of molecules with higher velocities here will be. What was my? Don't get me started. Don't get me started. Okay, you okay? You're already playing with fire. Don't get me started on the moles. Okay, all molecules have the same kinetic energy at the same temperature. Well, I'm stuck on this sentence, and my brain just refuses to process this information. Okay, fraction of molecules with high velocities increase as m, and thus molecular weight decreases. So this is molecular speed. Fraction of molecules within the 10 meters per second of indicated speed. Okay, so as we increase the molar mass, as we increase the molar mass, the fraction decreases. I'm stuck. I don't know. Ability, hold on. Let's read on, maybe we'll click. In order to retain a gas for the age of solar system, the average velocity of the gas molecule should not exceed about 1/6 of the escape velocity. Okay. Yes. Hydrogen molecules can easily achieve this velocity, and this is the reason that hydrogen, the most abundant element in the universe, is almost absent from its atmosphere. Oh, that's... Okay, I mean, so far... Okay, I get this. I get this bit. Although hydrogen is not significant as a component of water vapor is, a very small amount of diffusivity up about the atmosphere where intense radiation brings down the H2O into H2. Escape of this hydrogen from upper atmosphere amounts to about 2.5 times 10 to the 10th gram per year. Cool. I get this bit, which means that our atmosphere is the way it is because at our temperature, only certain molecules can achieve the velocity required to escape Earth. So other ones will stay. So because hydrogen is more spread out, it will escape. Because oxygen is more like this, it will stay because it can't achieve the, you know, the high enough velocity. I get that much. I get that bit. Hold on, what has higher molecule? What has higher molar mass? Oxygen, right? Okay, I think I get it. So the higher the molar mass, the sharper it gets. Because yeah, oxygen has higher molar mass. It's a heavier particle. Ah, damn it. Okay. The higher the molar mass, the sharper the heat. I think so. I'm like 73% certain. Derivation of the ideal gas equation. The ideal gas equation of state came about by combining empirically determined ABC laws of Avogadro, Boyle, and Charles. On the terms of kinetic molecule theory was the derivation of this equation from simple mechanics in the late 19th century. This is a beautiful example of how principles of elementary mechanics can be applied to a simple model to develop a useful description of the behavior of microscopic matter. We begin with recalling that pressure of a gas arises from the force exerted when molecules collide with the walls of the container. This force can be found from Newton's law. This. Cool. So force is equal to mass times acceleration. That's like about as basic as you get, and then and then acceleration is broken down as the derivative of velocity. Makes sense. And which v is the velocity of a component. Yeah. Then we have a graphic which what's the difference between these two? No idea. Okay, to evaluate the derivative equation 1.4.4, so this one, which is the velocity change per unit time, because there's a single molecule of a gas contained in a cubic box of length L, I think. For simplicity, assume that the molecule is moving along the x-axis, which is perpendicular to a pair of walls. So this is so that it is continually bouncing back and forth between the same pair of walls. When the molecule of mass m strikes the wall at velocity plus v, and that's with momentum mv, makes sense, it will rebound elastically and end up moving the opposite direction with negative v. Makes sense, because it's bounced back, so it goes forward, it bounces back, and it goes the other way at the same velocity. Energy conserve or something, I don't know. The total change in velocity per collision is thus 2v, and the change in momentum is 2mv. Yes, so force is equal to mass times acceleration, and since at that moment, instantaneous derivative, that's a great thing to say, make it, but at that moment, the instantaneous derivative would be equal to 2v, which means we get 2mv, and so that should be the force. The frequency of collision. After the collision, the molecule must travel a distance L to the opposite wall, and then back across the same distance before colliding again with the wall in question. This determines the time between successive collisions with a given law. The number of collisions per second will be v divided by 2L. The force F exerted on the wall is the rate of change of the momentum given by the product of momentum change per collision constant frequency. Avogadro carried, in my opinion. I don't know. I don't like walls. Not a fan, you know. Not a huge fan. Hi there, Jake. Hi, welcome to the live stream. Okay, pressure is for. Okay, hold on. Let's break this down. We have 2mv, which we know is from this derivative. So we have big F, which is equal to derivative of mv, which means just the velocity times mass. I forgot the unit. Momentum. So derivative momentum in relation to time is equal to 2mv times why v divided by 2l? Oh, because this is vx. Wait, why v divided by 2l? Rate of change momentum given by product momentum. Pressure is the force between energy, pressure P exerted on the molecule of the wall. cross-section L squared becomes. Your cap is very distracting. Sorry. Sorry, it has to stay. I'm just slinging nothing around with this. What am I to do? It's liquid. We're learning about the physics of... Well, we will soon be learning about the physics of that. I can't control liquid. That's just what liquids do. They splash. Why Vx divided by 2L? This is the time between successive collisions with a given wall. Number of collisions per second. This is because this is a number of collisions per second. Make it get together. Okay. Makes sense. So the force is a number of collisions per second times the momentum or the kinetic energy in this case, right? That's what okay, so the kinetic energy per collision times the number of collisions. So basically, and okay, this is gonna be careful when you're in the graph. Oh, you're so right. There we go. Okay, almost splashed it all over. Okay, this is actually pretty cool. This is pretty cool because we have. Let me show you what we all got. So we have force, all right, force per collision. And then we multiply it by collision per second. Wait, not force. Right? No, not force. Energy. I meant energy. This is energy. I think. I'm like solidly certain. Which means that we cancel these two units and we end up with energy per second. This. So this will be equal to Einstein. Pressure, okay, pressure is the force per unit area. So pressure P exerted by the molecule on the wall of cross-section L squared becomes this divided by L squared, which gives us mv squared L cubed. Or in other words, it gives us mv squared divided by volume. This is really cool. This is really, really cool. I love this, honestly. I love it so much. All right, so I wanna, you know what? I'm gonna note down all these equations. So we have F is equal to ma, which is equal to m dv dt. Once again, force is equal to mass acceleration. Basic very much. Okay, I can't scroll down and need the rest of this. Once again, force is equal to mass acceleration, basic equation, which is and acceleration is just the derivative of velocity in relation to time. Then the next equation. You know what? I'm just gonna give myself some space here. There we go. So we have the next equation, which is this. So force is equal to the derivative of, well, okay, so force is equal to the derivative mvx by dt. So it is equal to the momentum in relation to time. Okay, force is the momentum in relation to time. There we go. Now, what is this momentum in relation to time? Well, I'm so glad you all asked. It is equal to 2 mv. So 2 mv in this case being, hold on, times vx L. So in this case we have 2 mv, which is the momentum per collision, and then we have vx to L, which is collisions per second. And so because of that, if we multiply momentum per collision with the collision per second, so like this, we get mv squared x divided by L. So momentum per collision times collisions per second equals momentum per collision times collision per second equals momentum per second. This cub is really getting in the way, isn't it? You're right, it really does look like... I mean, yeah, because that's what it is. I'm currently reading one topic. Can you explain to me, you know, anything about it? Topic is spintronics in quantum physics. No, I do not know. No, sorry. I don't know that much. I'm only like a weekend quantum physicist, let's call it. So someone who just, you know, does quantum physics for, well, doesn't really do quantum physics, just researches quantum physics for fun. So I'm very much a weekend researcher. So yeah, I don't know much. So I'm really sorry, but can't help you. And so we have this, which is momentum per second, which is equal to mv. It's really cool you can just derive that. Isn't math sick? That's our momentum per second. So now we have pressure is equal to force. Wait, hold on. Force divided by area. And thus we have this, which is the area is of course L squared. And then top one is this. That's what we get. And so pressure will be equal to this. We have pressure in relation to volume, which I think is really cool. One strategy of this video is that math is a platform to create conscious extends experience as any other form of communication. Would you agree? Well, not quite what that video was about, but in my opinion, math is just notation. That's it. Just a form of notation. I don't know if I wouldn't be exactly count it as a form of communication like that, because math is specifically designed to not require any intelligence when it comes to interpreting it, which means that math is designed so that there will be no ambiguity. So I would rather call it I mean, yeah, it would be like a form of communication, but it would rather be like a notation for communication. So a standard for communication with no ambiguity. I suppose that's a very fair way to put it. And yeah, hold on, where are we? Volume, sick. Pressure produced by N molecules. Alright, so we have this, which is cool. I mean, come on, isn't that cool? We can derive, I'm sorry by the way, I know my huge cup of coffee is in the way, let me just move it to the corner. Isn't this cool by the way? We can derive, based on just some really basic, and I do mean really, really basic physics, like this, we can derive all of this and get the pressure in relation to volume. Alright. Pressure produced by N molecules. As noted near the beginning of this unit, any given molecule will make about the same number of moves in the positive and negative directions. So taking a simple average would yield 0. To avoid this embarrassment, we square the velocities before averaging them, and then take the square root of the average. The result is known as the root mean square velocity. We have calculated the pressure due to a single molecule moving at a constant velocity in a direction perpendicular to a wall. If we now introduce more molecules, we must interpret v squared as an average value, which we will note as v bar squared. So it was the same one. Okay, good to know. Also, since the molecules are moving randomly in all directions, only 1/3 of the total velocity will be directed along one Cartesian axis, and so the pressure exerted by n molecules becomes n divided by 3. So n divided by 3 times mv bar squared divided by volume. Okay. It's not important, it's not even fully completed. Yeah, I'm not an expert. I can't stress that enough. I will be working with experts a lot from now on. My next video will be with an expert. Foreshadowing this week. Stay tuned. What day is it today? Friday. Well, this week is a hopeful promise, actually. Might be Monday, might be Tuesday. But it will be with an expert. So I just want to make that clear. I'm not an expert. And so I don't really know all that much about quantum mechanics. I'm only a poser who researches weird things on stream. Alright. I gotta go. Short stay today. Bye. See ya, Ramit. See ya, and good luck. How long have I been streaming for? 40 minutes. Oh, I've barely gotten through a chapter. Cool. Okay, so we have pressure, which we can denote as volume, because that's what it is, right? Length cubed. M this, oh wait, no, this length. I have no idea what I'm explaining. Honestly, yeah. You know what, just good enough. MV squared, it looks like negative underscore 2, but good enough. And then we'll have fraction divided by 3n. And right there we will have n is just the number of molecules, and then we have 3 because 3 coordinates. Sometimes I think you are a VTuber, but knowledgeable VTuber. The best VTuber on science YouTube. How many VTubers are there on the scientific side of YouTube? I might be one of the pioneers. Knowledgeable VTuber. I mean, not really. I just have a textbook on the screen. I feel like that's my knowledge. It's right there, written by someone else. I mean, I'm not hiding it. The above statement that 1/3 of total velocity of molecules together does not mean that 1/3 of molecules themselves are moving in each of these directions. No, each individual particle is free to travel any possible direction. Makes sense. Like, if you have a particle moving in some direction, you just have to break it down to 3 separate coordinates. And because of that, on average, each one will be 1/3. Makes sense. Particle is free to travel any possible direction. Then can be regarded as composed of 3 components that correspond to 3 axes. There we go. Exactly what I said, precisely sick. The red arrow and the illustration depicts the path of a single molecule that travels from point last quadrant to the origin. Okay, temperature of a gas is measured is a measure of the average translational kinetic energy of its molecules. So we can begin by calculating the latter, recalling that mv squared divided by 2 is the average translational kinetic energy. Epsilon. An epsilon. We can rewrite the equation. Question mark, sick. Do you like studying on stream, or just in general, or has it turned into a sort of obligation for you? I mean, all of them could be true at once. Like, all 3 of those statements could be true all at once. I do like studying on stream in general, and it is an obligation. I've been doing it every day when it comes to studying. I've been doing it every day for a week now. When it comes to streaming, I've been doing it every day for a year and a half. It'd be silly to stop now, right? Can you imagine if I just finished it off at 436th day? That'd be silly. I have to keep on going. Yeah, I mean, when I research stuff alone, I do it in the exact same way. I talk to myself. I pretend as if you all are still there. Because I just can't do things like that. I don't know. So might as well stream. You know, if I'm talking to myself, might as well stream. Music. YouTube, please. There we go. So we can write the equation as pressure. Wait, is that pressure times volume? I think it is. Pressure. So we multiply both sides. Okay, so let me just take this for a second. And we multiply both sides by volume. And so we get multiply both sides by volume. This. And then if MV, oh, it's really inconsistent notation. I don't like that. I've been over this when it comes to quantum mechanics. We've had some inconsistent notation there too, and it was really upsetting. Average translational kinetic energy. But I know you're hiding your real identity and knowledge. I'm not hiding my real knowledge. I'm not that smart. Epsilon. It is an epsilon. Never mind, I'm a genius. Okay. Which means this would be equal to... It would be equal to broken latex, apparently. MV... Hold on. M... bar V square, which will be equal to 2/3. So we multiply by 2 because epsilon times 2 is equal to mv squared, which means this would be equal to 2/3 n epsilon. Neat. The two-free proportionality, the two-free factor in proportionality reflects the fact that velocity components in each of the three directions constitute 1/2 kT to the kinetic energy of the particle. The average translational kinetic energy is directly proportional to the temperature. Okay. Okay. Okay, so... Kinetic energy is the average translational kinetic energy. Epsilon is equal to 32 kT. Or something which I think is much more important. Epsilon. Well, it's not really much more important. It's the same thing, but this. Epsilon is proportional to true temperature, was it? I think. Okay. Notice that the equation looks very much like the ideal gas equation. Yes. Okay. But not quite the same, however. We have been using capital N to denote the number of molecules, whereas N stands for number of moles. Which is so much different. Number of molecules and number of moles. I'll make videos of space. We're getting there. We are getting there. I will make videos about space. Lots of videos about space. It's just that right now I am in my chemistry era. For now. At the moment. I'm finished with my quantum mechanics era, and right now I'm moving into my chemistry era. Then we'll go through the electricity era. And then we'll go on to broader physics, and then just everything. Space. Everything. But it's not quite the same. I have a number of molecules where n stands for number of moles. This is just this. Yeah, it doesn't matter. And of course, proportionality factor is not the gas constant R, but rather the Boltzmann constant. The Boltzmann constant K is just the gas constant per molecule. So for n moles of particles, then they are all friend. The ideal gas equation say came by about combining the empirically determined laws of Boyle, Charles, and Avogadro, but one of the transmechanical molecule theory was the derivation of this equation from simple mechanics in the late 19th century, as we just did right now. Are we going to have a Shakespeare era? What would that even look like for my videos? This is a beautiful example of how the principles of elementary mechanics can be applied to a simple model to develop useful description of behavior of microscopic matter. And it will be worth your effort to follow and understand the individual step of derivation, but don't bother to memorize it. We just did follow through without memorizing anything. Look how smart we are, everyone. We're so intelligent. Okay. This is the last bit, which is how far does a molecule travel between collisions? Finding ideas is obviously everyone has some different ideas in their mind related to any topic. You obviously have some. What topic? I want to see you acting out Romeo and Julie with Susie. Or is it Susie now? Oh, you creep. No, you're acting really weird this live stream, I've got to say. What's gotten into you? Like, all of these weird thoughts, calling me little, which is a very mean thing to do, sir. I'm sorry, I'm a bit cranky. I woke up, I just woke up and I started, I'm a bit cranky, it's not me, I'm really sorry. I thought that maybe kinetic molecule theory would help, but for some reason it didn't. Apparently it just made things worse. Okay. Oh, we're almost through a sub-chapter of a sub-chapter. In... how long have we been streaming? 50 minutes. 50 minutes for a single sub-chapter of a sub-chapter. That's quick. Molecular velocities tend to be very high by everything standards. Typically around 500 meters per second, which is insane. But even in gases, they bump into each other so frequently that their paths are continuously being deflected in random manner, so that the net movement, diffusion, of a molecule from one location to another occurs rather slowly. How close can two molecules get? The average distance of a molecule moves between such collisions is called mean free path, which depends on the number of molecules per unit volume and on their size. To avoid collision, the molecule of diameter sigma must trace out their path corresponding to the axis of the imaginary cylinder, whose cross-section is pi sigma squared. Eventually, it will encounter another molecule, extreme right in the diagram below, has intruded into the cylinder and divides emptiness of its free motion. How, the voice in my head or something, I don't know. The volume is in the pi sigma squared that's such a... I love it. I love how when mathematicians really get going when it comes to the Greek alphabet, they just forget letters exist. At all. Okay, the volume of the cylinder is pi sigma squared lambda. That's lambda, right? Or delta? Wait, is that delta or lambda? I think that's lambda. Yeah, okay. What's delta look like? Yeah, I'm silly. Delta has a... okay. Yeah, once mathematicians get going, there's no stopping. It's just sigma, the pi sigma squared lambda. At each collision of the molecule is diverted to a new path and traces out a new extrusion cylinder. After colliding with all n molecules in 1 cubic centimeter of the gas, it will have traced out a total exclusion volume of pi sigma squared lambda. Solving for... okay, this makes sense. So the cylinder goes this way, basically. So we can't see... okay, this is actually the cylinder, okay. Solving for delta and applying correction factor of square root of 2 to take into account the exchange of momentum between the colliding molecules. The detailed argument for this is too complicated to go into here. Boy, if I had a dime for every single time I had that before. We obtain lambda is equal to 1 divided by square root of 2 pi n sigma squared. Small molecules such as helium, hydrogen... No, wait, that's two of them hydrogens, and carbon with 4 of them hydrogens, typically have diameters around 30 to 50 picometers. At SDP, the value of n, the number of molecules per cubic meter, is standard temperature pressure, I think. N is equal to this, which is a constant. Solving for... Wait, inverse mole divided by inverse... Oh, because this amount. Mole is such a dumb unit. I hate it. No, mole is not a unit. It's a constant. Solving for this for the mean free path yields a value of around 250 nanometers for the mean free path of the most molecules under these conditions. Although this may seem like a very small distance, it typically amounts to 100 molecule diameters, and more importantly, about 30 times the average distance between molecules. This explains why so many gases conform very closely to the ideal gas law at ordinary temperatures and pressures. On the other hand, at each position, the molecule can be expected to change direction because these changes are random. The net change in location of molecules experienced during a period of 1 second is typically rather small. Thus, in spite of high molecular velocities, the speed of molecular diffusion in a gas is usually quite small. Today, my teacher challenged to simplify 1 divided by 1 minus 2 square root of 2. Then, what if root 2 is cube root 2? Which is basically asking us to find the pattern. Actually, she couldn't answer why. Cube root 2. I don't understand. I'm not gonna lie. Okay, 1 divided by 1 minus 2 root 2. 2 square root, basically. What if root 2 is cube root 2, which is basically asking us to find the pattern 1 minus b power of n. No, I'm sorry, I don't understand. Wait, so she turned the... That doesn't help. She turned the square root into a cube root? I'm sorry, I don't understand what happened in general. Okay. Oh my goodness, we're done with the 5th chapter. It got such a long time. And this one has 5. Okay, but this one is kind of great because it's chemical bonding, molecules. I'm actually... Oh, I don't think we'll need to research this all that much. I'll still leave it for the next live stream. I still will leave it for the next live stream. And yeah. I think that'll be it for today. I have a video to make. I finally can make videos. I'm finally done with the render times that take 70 years. Yeah, celebrate. I'm gonna celebrate by working on more videos. It's like I always celebrate. It's gonna be fun. 900 views, that's pretty good. That's really good, in fact. Oh, hold on, we also got some comments. I'm gonna reply to comments. You know what? That's a good way to end this live stream. I'm gonna reply to comments. Sorry for saying those things today. I'm tired. It's fine. I'm fine. Listen, it would take a bit more than that to actually upset me. Still be calling me little. That's so mean. All right. Hold on. Let's reply to comments. All of them. All that I can. No one streams. It's fine. It's all good. We're ending this live stream actually because we've already done the thing. Okay, hold on. We're looking for the ones I haven't read. Animation editing. I'm gonna see. Didn't hard so that because I have no idea how to reply. This is a phenomenal. I'm just gonna give him a shocker, shocked face. Where's the shocked face? There we go. That's gonna be my reply. Soda. For those who don't know, Soda is the one who made the music that's playing right now in the background. I said the music that's playing right now. I said the music that's playing right now in the background. There we go. That music. I've seen many of your videos and you always produce beautiful renditions on topics discussed that makes them more intuitive and easy to understand. However, personally, your videos are not quite rigorous enough to properly educate someone on any topic. I know that just wasn't the purpose of this video. I hope that your future content could include more rigorous dive into the subject. It will, collab video coming soon, that viewers could be able to investigate more or have more comprehensive understanding on the topic. And this is math series, a perfect place to start since more mathematical tools can be explained quite rigorously and properly taught without an overwhelming amount of prior knowledge like the other topics in the channel so far. Yes, that's precisely why I started the series and I really am excited for it. For example, you can give non-intuitive explanation of calculus and also give them a definition for derivative, give viewers a practical tool to actually do derivative calculus. That's recommended. Giving various levels of practical problem explanation problems. Yes, I will also do that. That's not the plan. Yeah, I'm so excited for the series. It's not ending yet. I'm saying, what? We're gonna answer comments first. Math. This guy, I remember this guy after he called excision. I'm pretty certain he completely roasted my lack of limits in my addition to quantum mechanics video. Okay, can't wait for future videos, neither can I. It is a platform substantiates our country's existing experience and form of communication. Oh, Jake, you! This is Jake joined in the live stream. Math is a way to round on reality. It assumes the world behaves in constant relation quantities. Like this. Math is an area of science that research quantities. Quantities of what exactly? It's not what we were. You know, fine. That's not the point of the video. What's math of science? I am in love with you. Platonically, I hope. I really hope platonically. You explained what's math. I have not. I have no idea if Robin is like replying to them or to me. I'm gonna let them do their own thing. But yeah, who's actually the first comment? The highest one. Just the two highest one. Complex analysis. I know why complex analysis is useful. I just used it as like a the point of the video was that the further it goes, the longer it goes on, the weaker the explanations get, and then in the end I'm like, you know what, I can't do this crap no more. I can't do this shit alone. I can't do this. So but that was the point of the video. Anyhow, a rainy day. What a song to end the live stream with. I suppose that for now that'll be it. Thank you everyone so much for watching, and have a great day. Bye.